The problem that we're looking at here is an L-shaped member which is supported by a ball and socket joint NO and by cables BC, BD, and AD. And these support are working against this applied force P, which is halfway between A and B. Our goal here is to determine the tensions that are carried by the three cables. In anticipation, we're going to be writing these cable forces in terms of XYZ components. My first task here is to be able to write out the unit vectors that correspond to these forces. So what I'm talking about here is I'm going to be writing a unit vector which extends from A to D, a unit vector which extends from B to C, and a unit vector which extends from B to D. And the reason for this is that in my FBD I'm going to have these three forces where this is the tension BC, the tension BD, and then the tension there of AD, in addition to a full set of forces here of OX and OY and OZ, which are supporting that member there at the ball and socket joint. So let's write out those three unit vectors. And going from A to D, I go a distance of 3D in the positive Y. I go a distance of 3D in the negative K. So I divide by the length of that. So that's the square root of 3D squared plus 3D squared. In the end, I get J divided by square root of 2 minus K divided by square root of 2. The unit vector which goes from B to D. I go minus 4D in the X. I go 3D in the positive Y. And 3D in the minus K in going from B to D. So then I divide by the magnitude of that, which is 4D squared plus 3D squared plus 3D squared. And so in the end I have minus 4 over square root of 34 in the X. I have a 3 divided by square root of 34 in the Y. And I have 3 square root of 34 in the minus K. So that's my unit vector which defines the direction there for the force of FBD. And then in going from B to C, that unit vector, I go the distance of 4D and the positive X, 3D and the minus Y, divide by its length, so that's square root of 4D squared plus quantity 3D squared. And so that unit vector is 0.8I minus 0.6J. I'm sorry, that's K for both of these. So please make that change. This is K and this is K. Okay, so I'm going to write down a moment equation about point O. I'm going to take a position vector which is going to represent the line of action of FAD and FBD. I'm going to choose a common point, and that is point D. Note that both of those forces act through D. So what I can do for my position vector, again, all I need to do is pick a point on the line of action of each one. D is the same for each force, and that R vector is going to be relatively easy to write down. So that's the unit vector from O to D. And I look at EBC. A simpler point might be to choose point C. So I will say that the R vector for that is from O to C cross with the force in cable BC, and of course I have the point P, which is acting midway between A and B. Let me call that point E. So this is ROE cross with minus PJ. So ROD, that's minus 4D in the I. It's 3D in the J. So I cross that into the sum of those two force vectors. So it's minus 4 divided by square root of 34 of FBD in the I. The J component, I'm going to have two terms of FAD divided by square root of 2 and 3 over square root of 34 for FBD. That's the J component of that resultant. And then for the Z component, that's going to be minus FAD divided by square root of 2 minus 3 over square root of 34 FBD in the K. And I still have the other two R cross Fs. The next one here is going to be, we said from, what do we say, from O to C. That's going to be 4D in the I, and that gets crossed with FBC, so that's 0.8 FBC in the I minus 0.6 FBC in the J. And then, of course, the applied force, that's at minus 2DI plus 3DK crossed with the applied force, which is in the minus Y. So there are a lot of terms here. What I get in the end when I set that resultant moment equal to a 0 for my I components, I get minus 3D of F80 divided by the square root of 2 plus 3 FBD divided by the square root of 34. That, in addition to 3 PD, that's what I get for I. Again, all I'm doing is R cross F those 3 times and grouping together my coefficients. For J, I get minus 4D times the quantity of FAD divided by the square root of 2 plus 3 FBD divided by square root of 34 plus 2.4 D times FBC. That's my J component. And finally, my K component is going to be minus 4D FAD divided by square root of 2. I have 3 FBD divided by square root of 34. And then I have a 12D FBD divided by square root of 34 plus 2PD. And that's a lot of terms. But what we know is that in order for that to be, that bar to be in equilibrium, that resultant is a 0. So each component is, and so for my first equation, I'm going to set this equal to 0. For my second equation, I set that term equal to a 0, and I set this one equal to 0. 0 for the third equation. And so what the order in which I'm going to solve these is I take equation 3, and what I'm able to get here is 4 divided by square root of 2. My d's can't cancel. That's a very small simplification. We get 4 over square root of 2 of f80. And for my fbd, I get 12 divided by square root of 34. And interestingly, I get subtract square root of 12 divided by the square root of 34 times fbd, and that's equal to 2p. So that cancels out, simplifies things. So I get the rather simple result here that f80 is equal to square root of 2 divided by 2p. So that's the tension in cable AD. And equation 1. Equation 1, therefore, is going to give us that 1 over square root of 2 f80 plus 3 divided by square root of 34 fbd is equal to p. And so what I get from there is that fbd is equal to 5/6 square root of 34 times p. And finally, my second equation, which is the J component of that moment equation. From there I get that when I solve for FBC, I find that that's equal to 5p. So the problem here really came down to writing out the tension forces in terms of its x, y, z components. That's the work right up front. And then we have to go through the effort here of doing R cross F for all the forces. I tried to save a little bit of effort here by recognizing that D is a common point on both the lines of action of FAD and FBD. O to D is a fairly simple vector. It only has 2 components rather than 3. So that actually saved a little bit of effort, as well as choosing point C for my reference point on doing the R cross F. Anyway, I did that, got 3 equations. It's just a matter of solving those 3 equations for the 3 unknowns of the 3 tension forces acting on that bracket.